Okay. Um, Bump this up a bit. Hello. Alright, there we go. Alright. Let me just I just have to do a couple things here. I'm gonna do this. I'm gonna be able to do this. Alright. Okay. All right. Yes. That's one thing. We can get into that. La da 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 da. Now we need to go to Switch. Login. I need to log in here. Get the code over here. Yeah. Right. All right. Now, testing 1, 2. Okay, it's a little bit low. I wonder if it's a Windows sound issue or a sound settings. I know. Okay. Test. All right, so that's a little better, right? Yeah. Okay, cool. So, welcome back to the Sunday morning paper. In today's edition, we will be finishing up our paper that we started last week on the Wigner function. All right, we're going to be finishing that one. And then later on today, I might be back for an encore in which we will be doing The Hobbit. So we'll be reading The Hobbit, chapter 3. Just try and get back into the swing of things here. I'm gonna take off the headphones so I don't have the feedback of having to listen to myself, which is awful. Yeah. Okay. Anywho, where was I? Right. Let's swap over to this here thing. Yeah. Okay, beautiful. It's gorgeous. Look at us there. And so I apologize for some of the weirdness. I have a new computer, and so I've been trying to get the stuff to work. Hold on, like, oh, no, why is this so high? Let's grab this down a little. There we go. All right. Yeah, so I've been trying to get all my stuff up and running again on this new computer, which takes a little bit. I'm not gonna lie. All right. It's on this side, isn't it? There it is. Okay. Okay. And we can see over here pretty well. Okay, good. There we are. Okay. So, here. Let us return to whence we were. So if we remember from last week, we were looking at these various transforms, and essentially what you're really doing is you're just kind of switching the variables. That's all you're doing. You're going from functions of time to functions of frequency, right? And you're going from functions of, let's see, for the Wigner function, Um, what was that transformation? So why are you being so? There we go. Sorry, trying to manipulate this on a new computer with a new setup here. So, let's see. So this is our Fourier, right. And now we're saying the spectrogram is over. Where's my pretty pens? Why no pretty pens? There we go. Yeah. Right. So we said in order to go right. So we've got our Fourier our Fourier transform by which we go from. Let's go up here. All right. That's a pain in the butt. Okay. All right. I have to tap instead of slide. Okay. So we start with the concept of the Fourier function by our Fourier transform by which we go from a function of time that is really thick. Okay. We go from a function of time to a function of frequency, right? That's all it is. It's literally just a transformation back and forth. From there, we say, okay, one of the main properties is that you can transform between variables all you want, right? But they have to physically have the same end meaning. So that means this has to be true, right? If you integrate over all time for a time dependent version, that's got to be the same thing as integrating all frequencies. For the frequency dependent version, it's the same baseline thing that you're integrating over it. You're just integrating in one variable versus another. They'd better be the same, right? You're just going back and forth. Good. Bloop. So the fundamental goal is to devise a joint function of time and frequency that represents the energy or intensity of a waveform per unit time per unit frequency, right? So ideally, you'd like to know you have some signal that's changing over time, and you want to know, all right, I have no idea what I'm clicking here, but at this time scale, what's my frequency content? All right, now at this time, what's my frequency content, right? Because they're going to be different as you go along. So ideally, you'd like to know per unit time, per unit frequency, what the content of your signal is that you're looking at. So fundamental goal, okay. The joint function we shall denote as P of T and F and necessarily satisfy the marginal conditions. Again, you've just right. You're still operating under a transform, the same Fourier transform. You're doing the same exact thing, but what you're doing is you're essentially multiplying that that signal by this window function, right? And so what the window function is, it turns out, this thing. This is a window function, right? And what it does is it ensures that at for any specific part of the integration, you're only looking at a specific time, right? And then later, you're looking at a different time, right? So this window function is sliding along. As it's doing so, it's zeroing out everything that's not in the window function. And so it's just looking at that window, right? Saying bam, 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 bam. I'm chunking along and I'm checking what the frequency content is here. Then I'm sliding over, checking what the frequency content is over here. Then I'm sliding over and checking what the frequency content is over here, right? That's what the window function is doing, which is why you're integrating over tau, which is a time variable, right? Because this is s here, small s is a function of time. But you're saying that's the overall time of my signal here, right? I have to integrate over that time. But my window function has a different time. And that window function time is the time of sliding. So t now becomes the time of sliding, and tau becomes the time of the actual function itself, right? So we integrate using this chunked window, and that is called a spectrogram. And that's saying when my window is centered at time t, then I will see this frequency content f, right? Cool. The window function w of tau minus t is centered at time t. The Wigner distribution for real transform S does satisfy the Marshall properties, is quadratic functional of the signal, and is defined as this. So what are we saying? Um, so A, we're taking our analytic version of the function, which we spent some extensive time going through yesterday. I'm not going to go as deep into that today, but it's an extension of the function into the imaginary with a look with an eye towards when you do the Fourier transform, it essentially cancels out all those negative frequencies, right? That are it's playing tricks with the mathematics to make the math work out, right? What we're looking is now rather than this window function here, which is sliding along, right? We now have the base function of our signal here, right? Which is sliding along in t, along with the complex conjugate of the base function sliding along in t in the other direction. Right? This is essentially a convolution of S with itself, right? But with this other sliding time in the same way we had a sliding time for the window function. Give or take. That's kind of what's going on. Right. So, um, S tilde again is the analytic function, which adds this imaginary component, which is just is put there to remove the negative frequency part of it, right? So that when you transform it, it comes out. Because normally, if you have a real valued function, if you take the Fourier transform of it, it's going to be mirrored positive and negative frequencies. Okay. So this gets rid of that mirrored aspect. Okay. The analytic function is used for several reasons. As is clear from the definition, the Wigner function is a quadratic functional of the signal. So it will, in general, exhibit interference between negative and positive frequency components of the signal. In other words, if you allow the negative components to be in there, you're going to actually affect the signal itself, what is calculating as the signal itself. And so your signal is going to start diverging from the real signal that you're looking at, right? So you can't apply this Wigner function without using the analytic, or you'll affect the core function that you're looking at. Because again, all of these are different translations of some core function that you're looking at, right? This is all this terminology and all of these transformations are all ways of looking at the same core mathematical entity, right? And that mathematical entity in this case is a common uh, direct descriptor of a physical state. And so that physical state is this signal that you're talking about, right? And so even this plot up here, you can kind of see uh even that plot up there is a graph of the signal, right? I'm plotting the amplitude of the signal at different points in time, where my amplitude is an estimation of how much power I have how much energy I should say I have in the signal. the waves themselves, of course, look a little different. So we're attacking these things that are removed, right? We're connected to these things that are removed, and because of that, we have to use these mathematical formalisms to discuss key characteristics of what this signal actually is. Um, and because we are doing things that way, that means sometimes we have to make these sort of moves where we're using this analytic version of, analytic transform of the signal, or Hilbert transform, I should say, of the signal to more accurately capture the reality of what's going on, while even though mathematically you're like, well, why would you need to do that? Okay. So, that is that. Okay. Oops. Okay. Ah. So he said that. All right. So an alternative definition for the Wigner function can be given in the frequency domain. Again, in this case, all we've done is we've gone back and forth between frequency and time. Frequency and time are interchangeable. Remember that, right? But if you're going back and forth frequency and time there, you have to go back and forth in frequency and time here. Right now, your your window, if you will, is moving in f, little f here, and your overall content is in nu, right? So we just transformed from the time of us sliding across to the frequency of us sliding across, right? So 1 over time. You can always transform between the two using the Fourier transform. So it's saying that, of course, the Wigner function is transformable in that way. The marginal properties are satisfied. And again, if we're saying that we're talking about a real function or real signal here, then transforming can't affect the core physical attributes of the function, right? So our total power has to be the same regardless. The Wigner distribution is time limited if the Wigner distribution is time limited if the original waveform is time limited, and frequency limited if the original signal is frequency limited. So, um, your signal can be one of the two. Either it's time limited or it's frequency limited, but not both. Okay? So, um, if you're in order for your signal to be frequency limited, to have a non-infinite number of frequencies composing it, in order for that to be true, it has to be infinite in time. In order for it to be finite in time, it has to have an infinite number of frequencies composing it. Now, those frequencies will very quickly, the amplitudes will get very, very small very, very quickly, right? And so you can functionally ignore them, when it comes to this, but they cannot be zero. Um, so you get to pick one of the two. And that's really the core. That part is that duality there, right, is the core aspect of um uh the brain. Why you have to go back and forth through these Fourier transforms, right? That is the uncertainty aspect of it, if you will, right? That trade-off is important. Anyway, the Wigner distribution is time limited. Okay. So if S tilde of t is if you were to multiply two signals, combine two signals together, then you integrate the two Wigner functions together, okay, over this dummy variable nu. Sure. Conversely, if S tilde of t is the integral dt, And that becomes the integral of t d tau. Let's see. So if it's just multiplying the two t's, vice if it's offset. So if this is a... So if this is a convolution, I believe this is just a convolution between the two. Then, okay. Here we're functioning, here we're, okay, sorry, just thinking for a second. It becomes integral to tau, because the integral of that d nu. Oh, okay, right, so these are just, yeah, right, so this is, we're integrating over frequency space here, right, and here we're integrating over, oops, we're integrating over time space here, right? We're integrating tau, which is in time space. So we're just integrating over different things. Okay. The Wigner distribution and the two-dimensional ambiguity function are a Fourier transform pair. This is kind of an important thing that's, for me, interesting. Because the ambiguity function is something that comes up a lot in radar systems, relating the range Doppler uncertainty, right? And so the fact that these are connected means I'm curious if you can screw around with things in the Wigner function and get results out on the ambiguity function side of things and use that to look at radar, to evaluate radar performance. Anyway, the two-dimensional ambiguity function is commonly used in the radar signal analysis as the most complete statement of the waveform's inherent performance. It reveals the range, Doppler, position, and ambiguous responses. So, in other words, it tells you, again, you end up with this binary choice, right? Either you are very precise in Doppler, which tells you the speed of what you're reflecting off of, or you are very precise in time, which gives you the location of the signal, right? So if I bounce a short signal off of something, right, I know exactly where that thing is. If I bounce a long signal off of something, it's somewhere in here. I don't know exactly where, but somewhere in there. So I can choose, right? But I need this long integration period if I'm going to get good resolution in Doppler. So I can choose either good Doppler resolution or good distance resolution, right? And so that is how the ambiguity function is used in radar systems. And so that is just a Fourier transform of this Wigner function. So that's, again, why it's interesting. So this is the ambiguity function, right? Which is a of nu and t. I'm sorry, a of nu and tau, s tilde of t plus tau over 2, s star tilde of t minus tau over 2, e to the I, right? So this, all we've done, the only difference between this guy and this guy, is we've converted between nu tau and TF, right? So we've just bounced back and forth between two different variables. So again, anything you do to one, you should be able to do to the other. Okay. Cool. Okay, so the following diagram can be constructed. And this is where we ended last time. So now let's continue. So yes, these are just Fourier transforms between the two, and A and P are in kind of opposite corners there. So, okay. Given that the instantaneous frequency f bar t is defined by the integral of the Wigner function times f over the integral of the Wigner function. And that should tell you the frequency at one specific point in time. Now, if we write the analytic signal in the form of S tilde is of t is the absolute value of S tilde. So that's right. So we're just since S tilde is a complex number, that means we have two components to it, right? We have our magnitude, our amplitude of our signal, right? And we have our phase. So we have our absolute value of S tilde times our oscillating portion of S. Then the above equation reduces to the well-known function ft. So the instantaneous frequency is just the phase information at t, right? It's just that oscillatory part of S, which of course makes sense, right? That's the part that's going up and down. So your frequency part is the part that's going up and down. Your frequency part is the frequency part. Cool. The time center at frequency f is analogously defined by that, but now you're multiplying by t in the top, right? Over the Wigner function, which is related to the derivative of the phase function of the Fourier transform. So if S to big capital S tilde of f equals what it is, then t, the instantaneous time center, whatever that phraseology means in this case, is just the is the oscillatory part of the frequency version of this function. Again, these functions are interchangeable because they're Fourier transforms of each other. They are interchangeable, so if you can do something to one side, you can do it to the other. Okay. The latter can be interpreted as the group delay at frequency f of the waveform. What does that mean? Well, the group delay, let's see. Usually in terms of a wave packet though. Let me see the best way to describe this. Give me a second. Give me a second here. Okay. Give me a second. Let's okay. Okay, blah, 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 blah. The group delay is a convenient measure of the linearity of the phase with respect to frequency and modulation system. For a modulated signal, the information carried by the signal is carried exclusively in the wave envelope. Group delay is therefore right. That's the envelope delay, right? Not very helpful. Okay, group delay is a negative derivative of the phase, predicts the time delay between the amplitude of the envelope of a pulse. Yeah, right. Places amount of phase lag, a specific frequency experiences has units in degrees. It's just amount of time lag. Okay. All right. Oh yeah. I guess that makes sense, right? So I have a signal that's doing like this, right? Time delay, right? Or the group delay is the amount of time it takes for this to happen. The phase delay is the angular difference between these 2 points. If that makes sense, right? Yeah. So it's the amount of time that this so if you have something like this, right? This is kind of a wave packet that's moving along, right? the time it takes for this to move over here is the time delay. Um, the phase difference between as it's oscillating between this and this is the like that's the angular difference between the two. That's the phase delay. You know. Anyway, so the second moments of the Wigner distribution are somewhat less meaningful because Wigner distribution is not definite. For example, sigma squared of f t is the magnitude of f squared t minus f magnitude squared, or I'm sorry, is the average of ft squared minus the average of ft squared is 1/2 the second derivative of the natural log of s, is independent of phase, but in general is non-positive. Thus, the second moment cannot be considered as a true variance. Okay. The most serious problem with Wigner distribution is that it is a nonlinear function of the original waveform. This has significant consequence on the output when the waveform is a sum of two or more independent components. Okay, that's interesting. It is. Thus, if S is S1 plus S2, then oops, we are not at the bottom yet. P Wigner is P1 plus P2 plus these overlaps, right? These is not purely additive. Where the cross Wigner distribution is defined as this. So S1, S2. So okay. That makes sense. The cross term is pairing the Wigner distribution of a multi-component signal pose serious problem for such signals. For example, the sum of independent narrowband components. Methods must be devised to minimize contribution of the cross terms. Okay. So that's one reason why it might be less useful to use for this kind of case, because you can't just add signals together. Okay. Useful relationship that relates the Wigner distribution to a linear project of two signals has been applications in detection theory. I'm sorry, and has applications in detection theory, is Moyal's formula, which basically a Parseval's identity. So it's saying the magnitude of the integral of s tilde 1, s star tilde 2 squared, right? If we integrate that and square the absolute value, that is equal to the double integral over t and f of the two Wigner functions. Okay. To discretize the equation defining the Wigner distribution, we begin with the ambiguity function and write it as in the following equivalent form. Wait, what? I feel like something is missing there. Okay. I guess that's just its independent thing, so this is different. So we say that's a useful relationship, sure. And then we just hop over to here. Interesting. Okay. Let's continue. To discretize the equation defining the Wigner distribution, we begin with the ambiguity function and write it in the following equivalent form. A of nu and 2 tau is integral s plus s minus. So instead of, okay, so what we've done is we've kind of recentered, right? Instead of saying, if we go back to our old ambiguity function, it was tau over 2, and now we're saying we're just renamed it to 2 tau for convenience. You may now discretize according to t is L times delta t, or t goes to L times delta t, and little t goes to n times delta t, where L and n are integers. So they're supposed to be, I bet you one of those is supposed to be tau, huh? Yeah, one of those is supposed to be tau. Which is supposed to be tau. Okay, so looks like T, this is T and this is supposed to be tau. All right, so there was an error in the paper. The whole paper is terrible. Sorry. All right. Right. So if we go like that, then we've discretized it. We've said we're jumping by some delta t, and we have L delta t's in tau and N delta t's in t. So our integral then becomes a sum because we're no longer a continuous function. We're just summing over discrete components, which gives the following equation for the Wigner distribution. Okay, the Wigner of N delta t f is 2 times the integral. So again, what we've said is, oh, well, this is just the Wigner function is just the Fourier transform of the ambiguity function. So we can get the Wigner function by taking the Fourier transform of the ambiguity function, which we've just discretized. So we do that, right? And we get the Wigner function here. For discrete frequencies, we will clearly have frequency aliasing. So best way to describe for aliasing. Aliasing is essentially if our window is too big, we start seeing repetitions of our signal. So our signal might look like this in frequency space, right? So this might be amplitude and this is frequency. If we go further along to, so if this is F1, if we go to 2F1, we will see our signal again, right? If our window is incorrect that we're looking at it in, we'll end up seeing these copies, and that's called aliasing. Right, so we're going to see frequency aliasing. To prevent this problem, we can either oversample. Yeah, this comes from a sampling problem. Your sampling starts lining up, so if I sample, let's see, here and here, right? I sample my signal here and here, and then I have exactly twice, right? And now I'm sampling here, or that's not actually twice. What am I doing? That is wrong, right? And it goes up, down, up, right? Now I'm sampling here and here. I'm getting exactly the same thing as this, but in reality, my frequency is twice as big because I'm no longer sampling enough times to actually see this smaller, right? I'm below my Nyquist frequency on my sampling here, so I'm not actually getting a real version of this. So it looks like I'm getting the same signal all over again, but now my frequency is supposedly 2 times it, right? So that's where aliasing is coming from. So we can increase our sampling rate, right? So we start oversampling this. We don't really need to sample that many times, but that will ensure that we get the correct frequency content for higher frequencies, right? So we can oversample our input data by a factor of 2 to, again, so that we're ensuring we're getting our Nyquist frequency at the 2x rate. Or use the analytic signal. That's the help of the analytic signal. You don't have to worry about that. Discrete formulation of the latter can be given in terms of the following discrete Hilbert transform. So that is the correlation to what we saw before with the Hilbert transform. which can be used in the construction of the analytic signal. Sn is S tilde of n is S of n times I plus I times the Hilbert transform of n of S of n. Okay. Okay. So let's just continue. So we can discretize it, which is good because anytime you're doing any actual work with it, you're going to be working with a discrete version, right? You're sampling a signal. You are performing calculations on the sampled signal, using a computer. You're doing these kinds of things. So, in reality, your integral is a sum whenever you're actually dealing with it. So it's good that we can discretize this Wigner function. That's helpful. All right. Cohen class of time frequency distribution functions. The relationship between the two-dimensional ambiguity function and the Wigner function and the Wigner distribution can be generalized to define a wide class of time frequency distributions. Indeed, the Wigner distribution is a special case, the more general class of time frequency functions parameterized by two-dimensional kernel function. Yes, in other words, what this is all saying is that, hey, look, our definitions that we have used previously, right? Let's go back up and look at our definitions here. We have defined these things that look really close to each other, right? We've defined where'd it go? We've defined this Wigner function, which looks kind of like this. And we've defined an ambiguity function, which looks very similar. We've defined a spectrogram function, which looks the same, except we have this other little function thrown in the middle, this windowing function that we've thrown in. These all look really similar to each other, right? So what if instead of this window function, what happens if we throw some other function in there? Right? I mean, it could be anything. It could even be a window function. So we can throw any sort of function we want into there. So that's what it's saying, that in general, as a whole, well, K can be anything. Could even be a window function, right? So clearly the Wigner distribution is just sets K equal to 1, right? Again, the spectrogram function sets K equal to a window function. So yeah, so the spectrogram also is a special case, corresponds to that kernel. To satisfy the marginal properties and ensure that the distribution is real, the kernel must satisfy the following properties. So at tau 0, if tau is 0, or if your function component is 0, then the whole thing has to integrate to 1. And if you take the complex conjugate of it, that means you have to just take the negative of all your components. In other words, your complex conjugate is symmetric over the kind of that point, really. If you go ft, if you think about it, it's essentially symmetric across this point. All right. So those are the requirements of K. Mayle's formula no longer holds valid, but instead the following equation is true. What is the following equation? Okay, so the magnitude squared of integrating whatever our signal is that we're looking at over all time, along with this complex conjugate, right? To remove when you in other words, review, yeah. I do my best to try and make these make some sort of sense. Um, so when we multiply it by the complex conjugate and integrate, what that does is it gets rid of the imaginary components. Right, the imaginary part of our function disappears. That's why we do it that way. You see this a lot in quantum mechanics, where the the actual probability of a wave function is psi star psi, right? I would integrate psi star psi. Same thing, right? It's that's why this is all interesting because we are looking at the Wigner distribution is used or can be used to give an alternate description of a quantum mechanical system. And this ambiguity function, these other functions aren't. They're used in other places. And so if the parallels hold, um, then potentially we could use some of the mathematical tools that we use on one side on the other side, theoretically, in general. Maybe. Who knows? Let's keep going. Okay. So we say that, all right, so that square, the magnitude squared of that is um so there's our two, we're integrating our two Wigner functions, but now we're multiplying by this other function Q, where Q is the difference between T and T prime, right? So again, we can think of this in terms of uh where these are still sort of like um uh what are they called? Convolutions ish, in that you have these two different versions of time. You have these two different versions of frequency that are offset from each other, and you're sort of by integrating, you're sliding these across each other and looking at how they line up at different points, right? Different points in time and different points in frequency, and you're looking at what these are doing at those times, and one's moving in t prime, one's moving in t, and so if it's moving in, and so this is correlating with point f prime, this is correlating with f, right? And these are sliding across each other back and forth. So, um, so that's what this offset is occurring. So essentially, you have the Wigner function of these two versions of each, right? And you're sliding them across, but you also have this intermediate Q. So what is Q? Q is um K, where we said K was our kernel, um, right? K was our kernel function, um, integrated over all of nu and tau. Okay, so we have to convert K. So K is not naturally a function of T and F, right? It's naturally a function of nu and tau. And so if we have to convert K into the appropriate variables to be able to apply this integral, right? Again, these are interchangeable. These are just different mathematical descriptions of the same core thing. So I can go back and forth between time and frequency as long as I do it appropriately, right? Thus, the strict Monreal formula is only valid when the kernel is identically unity, which we saw was true for the Wigner function. In general, the validity of In general, the relationship between the Wigner distribution and the two-dimensional ambiguity function now becomes double integral of a times k, right? Times k, where we are just essentially doing the two-dimensional Fourier transform. Again, these are two-dimensional Fourier transforms of each other, so of course, right? It's just the two-dimensional Fourier transform of a times k. That's it. That's all it is. The result is very important. It implies that the effect of the kernel function is that of a mask in the Doppler lag domain of the ambiguity function. Say it again. Implies the effect of the kernel function is that of a mask in the Doppler lag domain of the ambiguity function. It also provides a starting point for the computation P of k shown in figure 1. Okay. So a mask is generally kind of like a window of some sort where you're looking at a specific portion of what's going on, right? Um, so in the case of um a in the case of a um spectrogram, that mask is literally a window function. So it's zero except where you're looking at the window. That's one. That's back to zero, right? That's a window function. Um, in the case of the ambiguity function, that is one. So it's not actually canceling anything out, right? It's just saying it's not doing any sort of masking. Although technically it is a mask that just encompasses the whole thing, but you could theoretically mask it in other ways. That's interesting. I wonder if you could mask it in specific ways to get something out of it. Huh. That is interesting, huh? I wonder if you can play with that mask function a bunch. Anyway, okay, let's continue. Before addressing the issues of interference reduction for multi-component signals, I shall present some examples of the Wigner distribution for some simple signals that will motivate the discussion of the kernel design. Okay, so again, what is that? What is this K, and can we manipulate K to do something cool? Okay. The first example consists of two sinusoids at frequencies 4.5 and 9 kilohertz. So again, this is double this, so you would expect to see aliasing. If your sampling rate is too slow, added together. The second example is a linear chirp extending from 2.5 hertz at a rate of 2 hertz per second. So in other words, that's this one here, right? As you go later in time, your frequency also is increasing. That is a very commonly used signal in radar systems. In both cases, the sampling frequency is 32 hertz. That should be more than enough. These two signals with a small added random noise are shown in figure 2 and 3 respectively, right? So here is our two sinusoids added together here on the top one, and this is our chirp on the bottom one. Okay. All computations and images are produced using IDL from. Okay, cool. Figures 4 and 5 show spectrograms of the two data sets. So let's go down to figures 4 and 5. Where are you? Here we go. Spectrograms of the two data sets. So we have our. So if we look at how we're reading our spectrogram here, right? We've got this is time here, right? And this is frequency here. So we are seeing this here at 4.5 and this here at 9 each, right? So, and those frequencies start at about 6 seconds and they end at about 12 seconds ish. So, it's just saying that at second 6, this is the amplitude that you're seeing, right? And then our chirp frequency is a little bit different. All right, this is saying that as you are increasing in time, your frequency is also increasing, right? So you're seeing what you'd expect to see, which is this inclined curve, if you will. right? So those are what the spectrograms look like. Um, okay. Figure 4 and 5. Okay, notice in figure 3, the frequencies are resolved quite well, but the time, right, well, let's try that again. Note that in figure 3, that's this one, the time series, the frequencies are resolved quite well, but the time resolution when compared to the actual series in figure 2 is quite inadequate. What? So in figure 3, the frequencies are resolved quite well, but the time resolution compared with the actual time series in figure 2, I don't think this is figure 3. I think that's figure 4. Because this is this. Right? Because this is well resolved between here and here. Yeah. So there's a little bit of shenanigans happening there. Okay. The frequencies are well. Okay. This trade-off between frequency and time resolution is, of course, the main problem with spectrogram. The reason why other time frequency distributions have been sought. So again, this is the core, contest between them. Uh, the situation for the chirp is far worse. The spectrogram fails miserably. So again, if you look at the time series, it starts right here and it ends right here. It's pretty easy to see exactly where it starts and ends. And this is a bloody mess. Right? This is a bit wacky. Okay. Figure 6 shows the standard Wigner distribution of the two sinusoids. Um, Here is figure 6. Now we're looking much better in time, right? Much more resolved in time. But we now have this little guy here in the middle. Ooh, we have that guy. Okay. Um, so, well resolved in both time and frequency, but the image suffers from the crossed term ghost between the two frequencies. This is ghost precisely the sort of interference that we wish to minimize in the analysis of multi-component signals and the key two-dimensional Fourier transform relation between the generalized Cohen class of distributions and two-dimensional ambiguity function. All right. So remember when we said before that we have the problem of cross terms, right? It's not these aren't linear. You can't just when you add them, you don't just get the sum of the two, you end up with the sum of the two plus the cross terms between them. And so physically when you throw this into a spectrum analyzer, right? If you were to look at the results of that, you end up with this part in here, right? And imagine you're looking at a test equipment and you're seeing this extra thing there. That's not real. That is an artifact of the mathematics that is showing up. Okay? Um so we have to, and that's coming because of the nature of the kernel, right? Because we have because it's not linear, we end up with this extra term that shouldn't be in there. So we want to pick instead a kernel that will remove that cross term. Ooh, foreshadowing. Okay. Uh, we must look at the magnitude of the ambiguity function in figure 7. The contributions to the original frequency lie close to the lag axis, both ends of the Doppler axis. Its design strategy for most examples is not clear. The kernel function must have most of its energy distributed along the two ends of the Doppler axis. So what was it saying? So now we're looking at Doppler in Hertz, right? Because now this is the ambiguity function. So this is an ambiguity function, right? This is not the same thing as this, right? These are different functions. This is looking at Doppler delay, and this is looking at absolute frequency. Okay. So what we've said is, if we can separate these out in Doppler, we're able to the contributions to the original frequencies lie close to the lag axis at both ends of Doppler, right? So these here, right, are where most of the actual energy sits. Sure. All right. Two well-known classes of kernel functions can easily be made to satisfy the preceding design criterion. The Choi-Williams CW class is parameterized by a single parameter sigma and is defined as exponential of nu squared tau squared over sigma, or negative nu squared tau squared over sigma. Zhao, Atlas, Marx, ZAM class of kernels, ZAM, is of the form g of t times sine of 2 pi nu times magnitude of tau over a over pi nu, where the function g of tau is arbitrary. Is that supposed to be g of tau? It's supposed to be g of tau, I think. Is arbitrary, and the parameter a is a number greater than or equal to 1. Generally, the function g of tau is set equal to 1. Okay. The CW and ZAM class of kernel functions were originally derived. Interesting. So then those are very similar. Anyway, CW and ZAM class of kernel functions were originally derived based on certain mathematical conditions. For example, the ZAM kernel was defined in time lag, i.e., t tau domain, by requiring a finite time support for distribution, which led to a so-called cone-shaped kernels. Okay. The kernel in the Doppler lag domain is the Fourier transform of the above with respect to the time t variable, and as a result is exactly the form given for k-zam. The distribution. Okay, so what are we talking about here? Okay, zam kernel is defined in t tau. Log in seconds. Okay. So this is saying that tau is the Doppler delay, and t, so it's saying what's my Doppler look like at a certain time t, and that Doppler can change over time. Sure. Okay. The computation of the ZAM function can be simplified somewhat since the defining equation is reduced to p-zam. Is this k? Okay, so we're just summing over that. I'm wondering about the CW one though. Show one distribution to sinusoids using kernel. Yeah, see. Does it have the ZAM one? Ambiguity function as a chirp. Oh, interesting. Okay. All right. I think we're losing the thread here a little bit. Okay. Hey, no, it works. What isn't that? Oh, what is that? Anyway. Sometimes works, sometimes it doesn't, whatever. Okay. I think that means it is as good time as any to take a break here until next week. This is where we are. Next week, we will do the remainder of this paper for our Saturday morning papers. Our next paper will probably be something less math heavy, maybe a little more something else. What else? I'm not 100% sure. But we will continue this process, going through these papers. If there's any specific paper you would like us to go over, please throw a message in Discord. The Discord can be seen at the top of the screen. Um, Otherwise, I will probably be returning later on this afternoon for reading of The Hobbit. Exact timing of that, I'm not 100% sure yet. I will figure that out. Anyway, thank you for joining as we play around here. I hope you have a good afternoon. As I said, chances are we will come back later on for some Hobbit reading. I'd like to do that today. I do have some other stuff I need to get done today, so we'll see how that turns out. Anyway, otherwise, have a good one, and I will see you